Welcome, everybody. I'm very excited to welcome you tonight to our first community meeting to talk about our carbon capture pilot that we'll be doing at Dry Fork Power Station. We're very excited. I work for TDA Research, and my name is Sarah Rawl. And this is the largest pilot we've done with our technology up to this point. So we're very excited to get to this point. And then the next step is hopefully a commercial plant. And hopefully there'll be the market drive for that. And tonight we're going to tell you all about that. We're going to start out with David Gribble. Our program manager is going to talk about the project.
Thanks, Sarah. Let me just start off by saying thanks for everybody coming out here tonight. We're lucky we got some pretty good weather. As you all know, once we get into this time of year, anything can happen. We've already had, I think, 40 inches of snow in Denver a couple of days ago. So
you're lucky.
We're lucky, exactly.
Yeah, I agree.
So tell you a little bit about what we're looking to do here. This is the first phase of a program which is going to capture around about 23 megawatts or so of total CO2 coming out of the power plant over at Dry Fork Station, which is, as you know, just north of town here a little ways. To put that in perspective, that's about 6% or so of the total flue gas that comes out of the plant. So as demonstrations go in the U.S., it's actually a pretty big demonstration. It'll be the largest demonstration yet at Dry Fork Station, and by a large factor, the biggest demonstration that TDA has done of our technology so far. But as you can see, it's still much, much smaller than the power plant itself, at only about 6% or so. The whole power plant is a little over 400 megawatts. To put that into perspective. We have two main goals from a technical standpoint on the project, and the first is to capture about 158,000 metric tons of CO2 a year and do that at least a 90% capture efficiency. We'd also like to demonstrate about 95% during the test as well. Current goals are always kind of pushing out to even higher capture efficiencies than the 90% target. And then the other thing that we'd like to show is that we've got a sequestration ready CO2 product, which is a purity of at least about 95% pure CO2, so that it can then go to the next use down the stream. If you haven't ever seen it from a bird's eye view, this is kind of what Dry Fork Station looks like. This is the power plant here, and this is sort of a 3D mock-up of what our system will look like when it's all said and done and built up there. The main feature of this is 4 separate contactors where the flue gas is passed over a solid state sorbent material, which removes the CO2 selectively and lets the rest of the gas components go on through to the stack. They're reusable, so we load them into sorbent beds, and then we switch the bed one after another. As one bed is used up, we bring the next one online, and then we regenerate the bed, and so on and so forth. We have a cycle through our process. Yeah. So it's a big project, and we've got a bunch of partners. The first one that I want to highlight is the OSED, which is the Office of Clean Energy Demonstrations with the Department of Energy. They're the main funder for this. They're going to be about 70% of the total cost, with about 30% of the remaining cost coming from the cost share partners, including TDA, SLB, which is our sort of technology development partner. You may have heard of them as Schlumberger. They've rebranded as SLB. The Wyoming Integrated Test Center, which is the planned host for this. That's the test center that sits right next to Dry Fork Station. GR2 Engineering is our engineering construction procurement company, or EPC, for this. The University of Colorado out of the Denver campus will be helping with some of the life cycle analysis on the carbon. That's trying to understand how the total carbon utilization, sort of cradle to grave, is associated with this project. BKS Environmental is going to help us a lot with the environmental impact and preparing to do NEPA review, which is an important part of this project. And then the University of Wyoming School of Energy Resources are helping us primarily on the community benefits side, which is the main reason why we're here tonight. But they're also helping us out and related to the administration on the Wyoming ITC side as well. So they've got a couple of different hats in this too. So we wanted to give you a little bit of an overview of what the kind of project schedule looks like. This is a 4-phase project, and in total, as it's currently set up, it's about 6.5 years or so. Just kicked off at the very end of August of this year, so we're only about 2 months into the project right now. And we're in this first phase here, which is kind of the detailed planning and feed analysis. That stands for front-end engineering design work. It's about an 18-month phase. We're also going to be doing some community benefits and life cycle analysis work in this, along with some expanded technical economic analysis, which helps us to get a firmer idea of exactly what the costs associated with the carbon capture technology are. And then that should set us up well to move into the next 3 phases. The second of which is a 12-month period where we go through final financing to make sure that all project finances are lined up, and permitting to make sure that we have all the permits in place, both for construction, but also for operation, maintenance, all of those kinds of things taken care of. Some initial procurement may take place in that stage, but predominantly procurement and construction is phase 3 of the project, which is a couple of years of timeline after the next basically 1 or 2.5 years in phase 1 and 2. And then once construction is done, we move into shakedown, testing, and then eventually decommissioning. This is the short-term demonstration. Like I said, we're only doing about 5 to 6% of the flue gas out of Dry Fork Station. So as a result of that, we're not going to have a full-time presence at the ITC. When we're done, we're going to decommission everything and take it away, and it'll basically go back to the way we received the property and ready for the next test, or possibly a full-scale CCS deployment down the road. So if everything goes to plan, that's, like I said, about a 6.5-year total time frame. We hope that there won't be any delays. There are go, no-go decisions and stage gates in each one of those. So we need to show good progress towards all of this and keep both our funding partner at the Department of Energy happy, but also all of the rest of the partners in the project, the ITC, and hopefully the local community here in Gillette happy along the way as well. Go ahead, Sarah. So to give you a little bit of background about TDA Research, we've got about 130 or so employees right now. About 35 of those are PhDs, mostly in chemical sciences, chemical engineering, and other engineering disciplines. We're sort of a basic R&D company, although we put a lot of emphasis on the development side of our research, trying to move as many of the novel products and ideas that we're kind of coming up with and testing into actual commercial products as we can. We've done this pretty successfully over the years. A couple of kind of interesting things that we've done in the past include some direct catalytic H2S oxidation technology that we've developed. This one I think was originally deployed out in California. We have a spin-off product called Sulfa Trap, or a spin-off company called Sulfa Trap, which does sulfur purification products. This is mostly for cleaning up industrial feed streams. A lot of this associated with like the fuel cell industry, so things like hydrogen sulfur and other sulfur gases like mercaptans. These will poison fuel cells. So we've got a whole line of products which are similar in a way to some of our CO2 sorbents that help take this sulfur gas out so that the fuel cells won't get destroyed by the gas. And in some cases that includes odorants, the things that you add to natural gas so that it stinks if you have a leak in your house and you should be concerned. Several years ago, we were instrumental in scaling up fullerene technology. These are the carbon buckyballs that you may have heard of. At the time, we commissioned a 40 metric ton per year plant in Japan, which I think is now part of Mitsubishi Chemicals. At the time, it was the largest fullerene plant in the world. I think it's still one of the largest manufacturers of that technology. And then we've done a whole bunch of things in other areas too. We have ambient temperature CO scrubbers on all of the military's F-18 aircraft. It basically pulls CO out of the cockpit gas so that the pilots don't become intoxicated by the carbon monoxide while flying. That's an important thing. We're doing a lot of work on air separation for medical applications, including forward military facilities. We've got a special soap that we developed over the years, which is used to remove things like chemical warfare agents from military aircraft. It turns out to be great for other domestic aircraft as well. And then carbon capture technologies are a big part of our current portfolio and moving forward as well. So to kind of talk a little bit more about the CCS technology or carbon capture system that we're specifically deploying or hope to deploy in this particular project here at Dry Fork. This is based on a physical sorbent. Our physical sorbent is a mesoporous carbon material. In consistency, it's very similar to like a granulated activating carbon that you might see in like a charcoal filter for water treatment. Similar type materials are used very extensively in the water treatment industry. Ours has been researched and developed over the years and modified a little bit to add some special nitrogen groups. Those primarily enhance the selectivity, which allows us to pull out a little bit more CO2 and a little bit less nitrogen and other competing gases that are present in the flue gas. That's important to basically improve the economics of the system. So that's kind of the benefit of our carbon versus some other carbons that you could find. One of the other kind of main advances that we've come up with over the years is how we put the carbon into the bed and the contactor. What we've been doing most recently is something we call radial bed. Essentially, the way that works is the flue gas, in this particular instance, this was from a field demonstration in Norway, comes up through the center of the bed, kind of percolates horizontally through the bed, removing the CO2 as it comes out and then collects in the outside of the bed. The reason why we do that is that it gives us a very low pressure drop so that we don't have to use like a heavy compressor or anything to push all of that flue gas through the bed. We're able to do that at much lower pressure. That's important because one of the main drivers for the cost associated with this is moving the gas around. If we can use it close to the pressure that it's already coming out of the plant or, you know, whatever the industrial source is, then the lower the cost of the capture that comes out of that. The sorbent that we use is kind of porous. It is kind of granular, and that porosity sort of allows the gas to percolate through the material as well as just kind of moving around the individual granules. That gives us better utilization in there. Although it lasts a pretty long time, one of the things that's nice about it is when it's done, it's pretty easy to dispose of as well. Wouldn't necessarily stick it in any landfill, but it can basically be landfilled as opposed to having to go to some like hazardous material processing facility, which is kind of nice. So like I said earlier, what we're looking at for the Dry Fork Station test is essentially a 4-bed system. So these are a little bit bigger than the beds from that Norwegian test. These are going to be on the order of like 100 times larger, but we'll use 4 of them essentially. And like I said earlier, the way it's going to work is basically the flue gas, you know, will kind of come through the system and run through one bed at a time. When that bed becomes saturated, you can only pull out so much CO2 for a given load. And then we switch some valves, the flue gas will go into the next bed. And then while that bed is absorbing, the other bed gets kind of regenerated in a fairly complicated, about 5 or 6 step process. First, we knock down some of the pressure, blow out some additional gas, apply some vacuum to the bed, and then sweep a little bit of steam through the bed as well. And then we repressurize it back up and then flip it over. So that's kind of how the process works. The vacuum that we use is relatively mild. It's about 150 millibar. To put that in perspective, that's basically removing about 80% of atmospheric pressure, getting it down into that kind of a range there, 80–85%. And then from a steam standpoint, we use about 1.5 bowls of steam for every bowl of CO2. So that's on a volume basis. So one molecule of CO2 is about 1.5 water molecules running through there. By using the 4 beds, it's a continuous process, so we don't have any periods of time where we can't process CO2. We just keep processing it the whole time. One thing that's nice about this technology, and important, I think, specifically for the Gillette area, is that we don't need any water. There are some competing CCS technologies that use a lot of water. Obviously, water is scarce. It's all throughout the Mountain West region, whether you're Colorado, Wyoming, Montana, that's a scarce resource. So it's nice that we're able to basically use just the water that we need for the process is essentially already present in the flue gas.
What is the size of that unit? Is it 50 feet or 30 feet?
You can see this as an artist mock-up of an individual here. I think the total height of this is in the vicinity of like 50 feet or so. So it's a pretty good sized unit, but it's no taller than like the existing power plant to kind of give you an idea.
Thank you.
Yeah. How much